Okay, in this video we're going to explore the concept of connectedness a little bit further, in that we will establish a criterion that applies to a graph such that when the criterion is satisfied, then the graph is connected. So this is the criterion. If G is a graph with vertex set V and edge set E, and if for every pair of vertices x, y that are not adjacent with one another, it is the case that the sum of their degrees is greater than or equal to 1 less the total number of vertices in the graph, then G is connected. So if every time we can find an x and a y that are not adjacent, we see that the sum of their degrees is greater than or equal to the cardinality of V, the vertex set, minus 1, then it must be that G is connected. So what this does not say is that every connected graph has this property. Here's an example of one that doesn't. This is a connected graph with 1, 2, 3, 4, 5 vertices, and here are two vertices that are not adjacent with one another, x and y, and the sum of the degrees of x and y is 1, 2, because x has one edge coming off of it and y has one edge coming off of it, so 1 plus 1 is 2, but 2 is strictly less than 1 less the total number of vertices, which is 4. 1, 2, 3, 4, 5 vertices, 1 less the total number of vertices is then 4, and 2 is less than 4. So this property says that if every time we can find a non-adjacent pair that their degree is greater than or equal to 1 less the total number of vertices, then G is connected, it means that if G happens to have that property, then G is connected. But it doesn't mean that G has to have the property in order to be connected. So it's required, but it's not sufficient. So on the other hand, we'll look at this graph here and show that it's not required, but it's sufficient. Let's see. We have here a disconnected graph with 1, 2, 3, 4, 5, 6, 7 vertices, and if we pick two non-adjacent vertices x and y, we see here that the sum of their degrees is in fact less than v minus 1. So let's see, 1, 2 plus 3, 4 is the sum of their their degrees, and there are 1, 2, 3, 4, 5, 6, 7, and so 4 is less than 7 minus 1 is 6, and so we see that the condition is sufficient, but it's not required. Okay, so now we'll sort of try and prove this to ourselves, and we'll do it by supposing that G is not connected, and then showing that whenever G isn't connected, the condition is not met. So that means that if the condition is always met, then G must be connected. Okay, so suppose G isn't connected. In this case, there are subgraphs G1, we'll say, with vertex set V1 and edge set E1, and G2 with V2 and E2, such that the vertex sets do not intersect at all. That is, their intersection is the empty set, so they don't have any vertices in common. So what we will do is show that there exists at least one pair, x and y, such that the degree of x plus the degree of y is strictly less than the cardinality of the vertex set V minus 1, where V is the vertex set of the graph G. Okay, well, we just pick an x and a y that are in the two separate vertex sets for the disconnected components. And in that case, they're certainly not adjacent with one another because they're not even in the same component. And we notice that the degree of x has to be less than or equal to 1 less the degree, or 1 less the cardinality of the vertex set V1, because x can at most be connected to only all of the other elements in V1. It's not connected to itself, so it has to be less than or equal to the cardinality of V1 minus 1. And And the same goes for the degree of y. It has to be one less than, or it has to be at most one less the cardinality of v2 minus 1, which is the total number of vertices in the second vertex set minus 1, so that the sum of their degrees, now we're just going to do some arithmetic, the degree of x plus the degree of y must be less than or equal to v of 1 plus v of 2 minus 2. So what we've done is just add up v of 1 minus 1 and then v sub 2 minus 1 to give us v sub 1, v sub 2 minus 2. But notice that because v1 and v2 are both contained in the vertex set v, because they're both subsets of the vertex set of the whole graph, then the sum of their cardinalities has to be less than or equal to the cardinality of the vertex set v. And in that case, the degree of x plus the degree of y is less than or equal to v minus 2, and the cardinality of v minus 2 is strictly less than the cardinality of v minus 1. And that's exactly what we were trying to show right here. So what we showed is that when G is not connected, then it does not have this property. So that means that if G always has this property, then G has to be connected. And that's a criterion for determining whether or not G is connected. I think that's it. Okay, thanks a lot.